Thank you, thank you. So yeah, it's not the only stupid joke, so I hope you also like it as much as us. So I was thinking about having this title for the talk. Then I thought this one was even nicer. Even this one can also work as art. But then I remember Unix is a very serious topic, and I went for the very boring title that you have all read. So my name is Sergio. I work for Travis. I am the person in charge to bring stickers for you that forgot them. Because it was my personal mistake. I will personally post them to all of you if you give me an address. I'm very sorry about that. But let's talk about pipes. It's more or less safe to assume that most programmers know the very basics of pipes. It's something you can use to put together several commands. We have this command that lists the files, but we can filter them by piping the output into another program that filters them, such as grep. In this case, we are looking for the executable files, and we can even pipe it into another one that will count how many of them there are. This idea of having the output of operation as the input of the next one sounds very familiar to us as programmers, because that's basically what programs do. We define functions, we call them with arguments, and we get those results, and we pass them into another function. So that's how we would write the same example in Ruby. It looks weird because it's written in the other way around, but it does the same. It lists the files, filters them, count them. As I say, it's a bit confusing because it's written in the opposite order, but we can use variables for that. Now it's not in the opposite order. It does the same. We can even use object orientation to also write it in the correct order, or the order that makes sense. And even some languages have some syntax, this is Elixir, some specific syntax that makes it almost the same as the original. In any case, that has been all my understanding of pipes for years. It's one of the first things I learned when I started programming, and yeah, I kept using to get the output of one command and pass it on to the other without thinking much about them. What I want to show you today is that this simplification, which is very useful to learn and understand things, is a bit oversimplified. It leaves out a couple of details that are very interesting, and we are going to have a look at them. In particular, I want to show you 3 properties of pipes that make this so old invention, 50 years old, basically unchanged and still useful. So let's explore those properties. To show you the first one of them, we're going to start with an example. As you may know, each process in Unix has one input and 2 outputs. Both outputs are the error output, usually used for debugging, printing debugging messages or so, and a standard output. That is the one that we usually plug into the input of another process. This is the setup that I'm talking about. It looks like a complicated setup with a lot of lines and stuff, but thanks to pipe being such a good invention, it's really easy to implement. It's literally one character to implement that schema. So we have 2 processes, and the output of one is the input of the other one, as we were saying all the time. Since we are going to do the examples in Ruby, it's more like this. It's a Ruby program that writes and another Ruby program that reads. So how do those programs look like in our example? This is the first one. Nothing too special. What we have is we are going to print 5 lines to both outputs. Once to the error, once to the standard output. And at the end we are going to say, yeah, we are done with this. So something really, really, really simple. For the second one, even simpler probably. We are going to read lines from the input. We are going to print something about them for each of them. In this case, since we know that both outputs go to the same place, which is our terminals, we don't bother distinguishing what we print where. We print everything to the standard output. So what do we expect that happens when we run this? According to this simplified understanding that I always have and many of us could have, each program is the output of the first program is the input of the second one, so we could think that this would be the result. We print all the first program prints all the lines, the second one gets them, process them. It's not exactly like that. It's like this. This is what happens when we run those programs. What's going on here? Well, turns out that the second program gets the lines as soon as they are being printed by the first one. No need to wait for all of them to be generated. This idea can be called streaming, or from some other point of view can be called laziness, in the sense that as soon as it's ready, it's when we start processing, and has a couple of implications that become more and more important the bigger the amount of data that is passed from one process to the other. The bigger that amount of data, the bigger this implication. The first one is in memory consumption. With our simplified model, we need enough memory to store the intermediate results. But in reality, being a stream, each line can be discarded from memory as soon as it has been read. So the memory consumption can be as low as what's needed to store one line. We saw in Aaron's talk how he wrote a program to process, I don't remember how many gigabytes of output. All that output doesn't need to go into memory. It's processed line by line. So no matter how many we have in total, this is a schema of what is going on. Instead of being this, what I said I was expecting, all the lines being generated by the first process and then processed by the second one, it's more like each line gets generated and processed, generated and processed. So the results are stream. That's the behavior I wanted to discover with this example. And there is something interesting about this, which is I had never thought about this in terms as technical as calling it streaming, but it's something that I always knew, but I didn't know I knew, because I have done this many times. Many of you have, probably. Tail -f and a file is a command that monitors one file and outputs whatever lines get added to that file. This is very typical in Rails development when you want to see the logs. In this case, I'm piping the output of that program into grep to filter only the lines that contain the string post. And the interesting thing about this is that tail monitors the file and never finishes. It sits there waiting for the file to have lines added, and it's a process that it's infinite. It never finishes. That doesn't stop grep from filtering out and printing for me. So yeah, this is something that it's like, it has a very practical implication. We can have infinite streams that never finish, and that doesn't stop the next programs to read them. So what we have seen is that what I call the Ruby implementation of pipes, where I get the output of a method and pass it into the other, is a bit naive, because it's not realistic about what's happening. It doesn't reflect this property. So what does it take to make my Ruby implementation behave like this? Well, it gets a bit more complicated. We'll need to do some things. In case you don't know it, let me introduce you the enumerator class. It's a class in the Ruby standard library that implements more or less this behavior. What you can do here is that what happens in this example is that we create this enumerator, and when we create this enumerator, we can put things into it. In this case, I'm reading the output of the ls command and putting that output into the enumerator. And on the other side, there will be some other part of the program that reads that enumerator, and we'll get that output as soon as it's generated. So, for example, I have this ls command that puts things into an enumerator. I can have another method that I call grep that gets the output of the other process as input and reads it with each. And does the same again. It creates another enumerator and does its thing. In this case, it filters. So that's why it does this if with the regular expression, and returns another enumerator. And I can have another method that gets another enumerator and does the same. It reads it. In this case, this one doesn't return another enumerator, it just returns a total, because that's how a count behaves. How does this thing work? When I run it, as I showed in the first example. Well, it does what we said. First, it reads one line from the output of ls. Then, the filtering code is the next thing that gets read, because it gets the line as soon as we generate it. In this case, the filter discards it, so next thing that happens is that we read another line. The filter goes in, also discards it because it doesn't match, etc. until there is one line. Yeah, this line gets read, the filter goes in, and in this case, the filter matches, so it will output for the next method to get it, and that's why we read. Now I'm going to count it. Yeah, the result of this is 1. But it's at the very bottom of the screen, so you cannot see it. It's 1. Oh yeah, it's there. So yeah, now we implemented that behavior. This code that I showed is not beautiful and it's not simple. Maybe you can read it more slowly later to get to the details, but that's the whole point. Like, the point I wanted to show you is that things are not as simple as they look. We need to do some stuff. Pipes are not as simple as we might have thought. So, it doesn't work with bubbles very well. Sorry about that. For discovering the second property, we are going to use the same schema of processes. So 2 processes, one gets output for the second one, but we are going to do a small change in those programs. What we are going to do is the same, but it's going to be a slow operation now. So instead of just generating the line, we are going to generate the line, but it's going to take us 1 second to do it. We print as logs when we start calculating. We are just sleeping, but and we also print when we are done calculating and we send it. So it does the same as the example before, but it's slower. For the second one, same thing. It does the same as before. It just processes, which is sending it again to the output, but it's also slower. So before we tried to guess what was the output of this program. We won't do that again because we already know it. But what we are going to try to guess is how long does this take. With our naive interpretation of pipes that we were thinking before, we might say, okay, it's 5 items, we know this. There are 2 steps per item, we know this. Each of those steps take 1 second. So this is a very easy question, Sergio. It's 10 seconds. Well, that's wrong. It's 6 seconds. 6 seconds. What's going on here? You probably already guessed it. Pipes are not only concurrent, which is what we showed before, they are also parallel. Things happen at the same time. So this is what we concluded before that was happening. This is also a simplification. This is not exact. This is more what is happening. We generate the first item, the second process gets it, but as soon as the first process already generated the first one, it's already generated the second one, generating the second one at the same time that the other process is already processing it. So that's what happens, and that's why, if you count, it's 6 seconds. Each of those blocks being 1 second. So, second conclusion, second behavior that we discover is that they are parallel. The execution is parallel. Okay, now we get back to our Ruby code that doesn't do that. The code that we wrote before would take 10 seconds. It doesn't implement this behavior. Yeah, we need to do threads. It's how you do parallel processing in Ruby. So this is getting a bit more complicated even. What our new implementation of the methods will do, all the methods will do this thing. We'll initialize a queue. A queue is something that comes in the Ruby standard library. It implements that data structure. You put things on this thing, and you get them from the other side, and it's thread safe. So several threads can be operating on them, and things don't get mixed or whatever. So what each of the methods will do, it will initialize a queue, spawn a thread, which is immediate operation, so it will spawn a thread and return a key for someone else to read from it. What that thread will do is putting things into that queue. but that will happen in parallel to the other process reading the queue that we are returning. So in this case, this is the first method that runs ls and puts its output into that queue. The second one is very similar. It reads from the queue that got as input and applies the filter, and if the things match, put them in the queue that it's returning as output. And the last one is a bit different, because this one that counts lines needs to get them all before it can return. It cannot do a partial count. It needs them all, and that's why this one doesn't return the queue, but returns the result. So once again, this code gets complicated. It's difficult to read, probably difficult to get all the details now, but you can read it slowly later. The whole point is to see, if we keep implementing the behavior of pipes, our code that we thought was just one line and calling one method and passing the result to the other, pipes do more stuff than we have thought. That's the whole point. That's the next thing we learn. This is how this code works, which is the same as before, but now it does it in parallel. It takes 6 seconds to run the whole thing. So pipes are concurrent and parallel. That's what we discovered so far. Okay. For the last property we're going to talk about, we need to think a bit about what we discovered now. So we have several parallel processes that do work in parallel and pass output for the next one to process. An implication of this is that these processes are temporally decoupled. Each of them can have its own speed, performance, throughput, whatever you want to call it. In this example, we have one process that generates 300 items, lines per second. Second one that is only able to catch up with 100. And the third one, also 100, because it cannot do more, because it only gets 100 per second. It's a bottleneck. This kind of bottleneck can give us one idea, which is we can have more than one process per step to catch up with that. This would totally work. The last one can, again, do 300 per second because we have 3 processes doing 100 per second. This is something that is completely possible, both with pipes and with our Ruby implementation, but it's an idea that we want to explore today. Because in any case, they are decoupled, so we are never going to have this exact same throughput in all of them, so the problem remains. So if we run this pipeline, what will happen after this pipeline has run for 10 seconds? The first process produces 300 lines per second, but the second one can only handle 100. What happens to the other? What happened to the other 200? Do we lose them? We don't lose them. We know that we end up processing it all. So where are they? Well, they can only be in some place. They're accumulating, waiting to be processed. It can only be the memory. It's the only thing we have where we can store things. And it's probably not the best place for important data to be for a long time. This is a real problem. If you have implemented some kind of queue system with RabbitMQ queue that was mentioned before in another talk or things like that, you might have had this problem, and it's not a particularly easy problem to solve. There would be a workaround, which is if there would be any channel of communication between these processes in which the second process can tell the first one, hey, slow down. It's completely stupid that you keep sending me 3 times as much input as I can process, because the total time is going to be the same. It's totally stupid that you keep sending it. It keeps accumulating. Slow down. Send me 100. It's what I'm able to do. So send me just 100. This concept is called back pressure, and it's kind of difficult to implement in a way that doesn't couple all processes, because, as we said, the communication channel is only in one direction, which is the pipe, and there is not an easy way to communicate back this idea of calm down. Back pressure is called. So I would be curious to see how pipes behave in this scenario. So we are going to go back to our example that we are using all the time, our two processes that are connected via a pipe. But we're going to, once again, do a small change in our programs. So 5 lines are not enough to expose this behavior. So we are going to increase that number for our test. What we are going to do is we're going to send 15,000 lines. We are going to log it only one in 5,000 because otherwise we won't be able to see what's going on. But other than that, we are doing the same thing. We are going to generate 15,000 lines and send them via the pipe. As fast as we can. No wait. We are back in the first case. As fast as we can. The second one is still a bit slow. The second one processes 5,000 lines per second. That's what that sleep does, and does the same as the other one. It logs only 1 in 5,000, so that the output is not that big. So if we run this example, this is what happens, and this is very interesting. So before we have been able to process the first 5,000 lines, we have already sent 15,000, right? That's what we see there. But an interesting thing is that this gap doesn't keep increasing. We would have thought, the first one is sending faster than the second one can catch up. This gap will be bigger and bigger and bigger and bigger. But this is not what's happening. The gap happens at the beginning, but at the rest, for the rest of the time, it doesn't increase. The gap stays constant. I tried to plot this, and this is what's happening. At the very beginning, one process is much faster than the other. The blue one is much faster than the red one. But at some point, it catches up with some specific site. With the lines we were working, this happened before 15,000, as we said. And the first process doesn't send more. How did that happen? We didn't do anything for that to happen like this. Well, what happens is that the operating system, which is what implements the pipe, is allocating a buffer between two processes, and once that buffer is full, it blocks the first process from writing until the second one has made a space on that buffer by reading it. So that back pressure we discussed before, it's implemented for free in pipes. It just happens like that. Our Ruby implementation doesn't. Our implementation will not have this behavior. Once again, we will need to change, to explore how to change our example so that we can implement that behavior in our Ruby program. In this case, it's easier because in the same library that gives us the queue, it also gives us this second class, which is called sized queue, that when we are initializing, it accepts one argument, and it implements exactly this behavior. When there are this many elements in the queue, then the queue blocks the process from writing. So yeah, this change was easier for a change. So, summary. Pipes are concurrent. They are parallel, and they implement back pressure for free. So they make sure that this concurrency and parallelism doesn't end up blowing our program up by implementing this. Pipes are really good. This is what I'm saying. This is pipes are literally the best. You should go and change all your systems to use pipes to communicate. I will hold your beer while you do it. So, yeah, let's hold the horses again. Pipes are old. They are around for 50 years. They have accumulated some criticism and alternatives as well. I found this comment on the internet, a very good summary of this. I will give you a link for you to read it. The really important part is this. What we are passing between the processes is unstructured text. So there is not much we can do with it. We are Rubyists. We are used to not being very strict about types, but I would say that maybe everything is a string, it's a bit too far in that direction. Many things will become difficult to do when we have this kind of communication in which we can only hope for the best. Error control, well, I wrote the line, if there is any problem with it, deal with it, bad luck. So that's an example of things that pipes aren't very good at. So I am not saying that pipes are the best and we should do everything with pipes. We can use them when they make sense and when those behaviors are useful for us, but we need to be aware that they are not the solution for everything. So depending what you're doing, maybe it's not a great idea. So what did I just do with the last half an hour of your lives? This was not a talk about pipes. This was a talk about a couple of design principles or patterns that happen to make software powerful, robust, and maybe last 50 years if we can apply them to our programs. So yeah, maybe our programs can use them. That was all. Thank you.